All right, let's get started. I actually got distracted by something, but I don't even know what. Maybe it was making oatmeal. Sorry to make you guys just sit here and stew, wondering what was going on. This is our last meeting today, our last Zoom meeting. Makes me really sad, frankly. I'm feeling. It's just a terrible way, a very weird way to finish the school year. We're going to do a kind of a little mini lab. I'd rather have us end doing that than lecturing about something about chemistry. So if you guys could get your interactive notebooks out, and we'll set it up as a mini lab on the next page. I'll give you a moment to get that set up. Remember, with your mini lab, just open the notebook up. And here's the binding down the center. And over here is the setup stuff. And over here is the results of that setup. I'll give you a moment to grab your interactive notebook. I'm pretty excited about this lab.
I don't think your mic is on.
I understand that. Thank you. I'm pretty excited about doing this lab because it really does a great job of we could have actually used this lab to determine that it's P1V1 equals P2V2. Like, we don't even have to take that for granted. I mean, we can just actually experimentally determine this. So it's, that's one of the things I love about chemistry, is so often you don't actually have to take, kind of like my word for it. We can actually just go experimentally determine that that is the case, that this isn't something that you have to just take on faith. Like, so often, like stuff that happens in math or physics and biology, it's because someone said so. And you're like, well, how do we know? And you're like, well, I don't know how we know. Well, we can actually figure out that P1V1 equals P2V2 really easily. It's going to be fun. Just wait. So, you're going to have to come back. What are the materials that we need? It's pretty easy. We need a piston that has a movable or adjustable volume. So in this case, we're just using a 60 cc syringe. And a gas pressure sensor. And that's about it. Pretty easy. Procedure. We're gonna start probably at 40. Adjust syringe to 40 cc's. Then, and record pressure. So we're going to go to 40, and then we're going to like squeeze it down to 30 with the pressure sensor on, and then squeeze it down to 20, and then maybe squeeze it down to 10, but I'm not sure. It depends on how hard it's working. And then what we'll do, and we'll go like from 40 to 30, and then we'll reset everything and go from 40 to 20, and then we'll reset everything and go from 40 to maybe 10. I'm not sure we'll be able to get to 10. And then we'll reset everything, and then we'll go from 40 to 50, and then we'll reset everything and go from 40 to 60. We want to reset everything between each trial because there is some amount of leakage, and we kind of don't want that leakage to keep compounding because it'll really skew our data. Because what will happen is as gas particles leak out of the system, the number of moles of gas keeps changing. And so we want to have the number of moles be as consistent as possible. So we're going to kind of, after each trial, we'll reset to 40, remeasure it, check the pressure, and then do our next trial. So pressure, change volume to 30, 20, maybe 10, 50, and 60. Reset after each change, going back to 40 and opening system to reach equilibrium. And this may seem a little unclear. But once you see it, you'll be like, oh, okay, I totally get what's going on now. So don't worry too much about that detail. And then we need a data table. Now, it might be nice to know what the temperature is today and what the barometric pressure is, but those aren't going to change very much while we're doing our experiment. So let's look at our variables. Pressure, we definitely need pressure, check. Temperature, we probably don't actually need the temperature because the temperature right now will stay pretty consistent as the temperature as we go forward. I mean, that's not going to change in our experiment. The number of moles of gas. Yeah, we're going to try to keep that constant, so we probably don't need to check that. I'm going to say no on temperature. And then volume, that's definitely something we need to check. So what we're going to do is we're going to have volume at start be 40 cc's in all cases. And then we need the pressure at start. And then as we go from 40 to 30 is one data point. 40 to 20 is one data point. 40 to 10. So each time we'll be recording our pressure. So what's the pressure in ATM, pressure in ATM, pressure in ATM? 40 to 50, 40 to 60. All right, let's see what we get. Hey, before we get started, I want to tell you guys about an opportunity for next year. I've been doing some research with John Bussey on designing and making different kinds of glass with fermentation. And it occurred to me just last night, actually, that John's leaving and I have no one to continue on that research, and we still have research questions and to pursue. So if you're interested in doing independent research and basically having a class where you can do experimental research and design what you're going to be doing and basically carrying out your experiments on a daily basis, it's kind of, there's quite a lot of freedom with it. Mostly you just conduct experiments and see the results and then design new experiments for the next day and keep doing that. If you're interested in that kind of opportunity, would you please send me an email so we can figure out how we can make that work in your schedule? If you're planning on taking Math Sci and you want to do that research, you don't have to do anything. Just tell me when class gets started that you're interested in. Hey, I'm taking Math Sci, Mr. Wright, and I'm in your 5th period class and I want to do research. And it'll be like, fine, we'll just kind of excuse you from doing the other Math Sci stuff and you can focus exclusively on designing, doing your research project. So if that's something you're interested in, either send me an email or have already been signed up for Math Sci and then we can discuss it in the fall. Does anybody have any questions about what I'm asking or telling you about? Oh, maybe I should explain why we're doing glass research. One of the reasons we're doing research on glass is one of the goals in Math Sci is for students to learn about the theoretical aspects of a material, and then we make that material. And one of the things that I really care about is students being able to manipulate the properties of that material. So yeah, we can make metal, but then how do you manipulate the properties of that alloy so it gives you the material properties that you want? Or yeah, we can form concrete, but how do you change the properties of that concrete so it has the strength that you're actually looking for? And this whole started with glass. We wanted to be able to have students make their own glass for doing their own projects, but the glass recipes that we were working with just were not suitable. They broke too easily. They were too hard to cut. If you heated them, they exploded. They just were terrible glass. And so we wanted to be able to design a glass where students could mix sand together with other chemicals, melt it down, and then be able to pour that and then use that glass in their stained glass project. And that's the kind of where the starting point is. One areas of continued research are how do we color the glass to get different colors? We already have like blues and greens and yellows and browns and oranges, but there's a lot of other colors. Oh, purple, we can do purple and pink. And then there's also another area that we're trying to pursue is how do we polish the glass so that we can actually make optical glass and then we can form it into lenses or we can use it as filters. I don't remember if you guys remember when we did the flame test, how we used a didymium filter. Well, we have the chemicals to dope the glass to make it into a filter, but we don't have a technique for polishing the glass so that we can actually look through it. Those filters are incredibly expensive, like about $40 a piece. And so, but we can make that glass for like about 25 cents. And so we're thinking about making glass filters and then polishing them so we can look through them. Other areas that we're interested in pursuing is how do you make really big sheets of glass? Right now, we can only make glass that's about 15 centimeters in diameter. So a circle about, well, like the size of about a CD. So you can make glass about that big in diameter when we flatten it out. But we'd like to be able to make much bigger sheets, like the size of a piece of paper. And so we're looking into some different techniques for rolling it out flat or maybe pressing it flat. I don't know. It's really kind of fun to do research because instead of you having to sit there and take notes and memorize a bunch of stuff, you get to just do things and you get to try things. And sometimes it turns out to be a failure and sometimes it turns out to be wonderful. So I would encourage all of you to have some opportunity to do research in your life it can be incredibly gratifying and it's super interesting. So anyways, let's do this experiment and let's see what we get. Let's see if we got this going. Let's grab our lab quest here. We don't really need that. Let's see if we can. We'll just change this to 9,000 seconds so that if we do decide to run it, we're never going to run out of data. Perfect. Okay. All right. So we can see that the pressure is 1.032 ATM. And I'm going to see if we can get this off. It's a bit of an oversight. I grabbed the wrong connectors when I grabbed this bag. Let me see what I can do. Make work here. There we go. So now, this is quite important. In the pressure sensor, there's 0.7 cc's of space. So we're really starting at 40.7 cc's. Okay. So here we are at 40.7 cc's. I have it actually really close to 40.40. And now all we're going to do is watch this pressure as we go to 30. So I'm going to bring this down to 30 and stop it right there. So we're actually at 30.7 and the pressure is holding pretty close at 1.4739. So at 30.7, the pressure is 1.4, I can't remember what it was. Okay, 14582. 14582. Okay. So now what we're going to do is we're going to bring it back to 40. And so pressure at start is 1.1042. Okay. So now we're at 40 again. And now we're going to go down to 20. Oops. It's starting to get a little bit hard. I'm having to do quite a lot of work to get it to 20. 2.08. Oh, come on, stay at 20. 2.0803. 2.0803. And this is actually quite important because watch what happens as I hold it at 20. You're going to watch the pressure decreases slightly. And the reason why it's going down is we're leaking gas out of the cylinder. So that's why we reset it each time. So we'll bring it back to 40. And then I'm going to, let's do 20 again, 40 to 20 again. And that's pretty close to our original. And now we're going to go down to 20. And we want to kind of do it quickly. So 2.08. So yeah, 2.0803 was fine. You want to get to it really quick because the longer you wait, the more gas will escape. Let's try again. Right? Because I still don't really feel like I got it right. Let's try it this time. High confidence. Tack. Ready? 20. Boom. 2.2. Oh, that was higher. 2.2. All right, let's try it one more time. So we'll go to 40. We'll let the air in. So we're back to kind of an equilibrium with the outside, the gas in the rest of the room. Let's go to 20 again really quickly. 20. Yeah, I think 2.2 something is probably our best option. All right, let's try. I don't think I can go from 40 to 10. Let's get it back to 40. I think what's going to happen is we're going to just peg the machine. Like it'll max out when we get to, I suspect what's going to happen is that it's going to max out when it gets to like 15. And by the time we get to 10, it's like all of the data from 15 to 10 will be the same value because we have kind of like pegged the pressure sensor, because it has a maximum pressure that it can read. I don't know what it is, but I think we may just find out in a moment here. Let's just go to 15 to start with, because I have a pretty high confidence that I can actually get it to 15. So let's return everything back to atmospheric environmental pressures. And we're going to try to get to 15. Ready? 15, here we go. 2.5. 051. So we went to 15. We got 2.5051 ATM. That was pretty handy. And we'll go back to 40 and we'll release it and get everything back to atmospheric air pressure conditions. We'll try 10. I'm not convinced that I'll be able to hold it at 10 long enough to even read it. We'll give it a shot. You guys ready? Oh, hey, what's 1.4540? Oh, this one? Yeah, okay, sure. Okay, here we go. We're gonna aim for 10. See what we get. 1, 2, 3, 10. Nope, we pegged at 2.5051. So that's the maximum this can do. So let's not go. I'm now highly suspicious of this 15 because if we pegged it, we don't know when we pegged it. So let's go back to 40 and let's try 40 to 18, I mean, 40 to 18. Because I just don't, it would have been quite a coincidence that we actually get to the exact right place for it to peg. So we'll go from 40 to 18 and go. Yeah, so that was peg 2. So it seems like we don't really know when it's going to peg to its maximum, but it's sometime after 20 and before 18 apparently. So those are not real data points. Okay, so we'll skip those. We'll get back to 40. Let's go to 50 now. Let's see what happens when we go to 50. So we're at 40 now, and we're gonna go down to 50. Boom, 0.8828. All right. Let's bring us back to atmospheric conditions, and we'll go back to 40. Excellent. And now we're going to go to 60. You guys ready? Starting at 40, down to 60, and 0.7225. Now, honestly, it'd probably be a good idea to run these trials several times at each one and kind of take some kind of average. That would probably get you your best data. So we have our data that's 40.7 down to 30.7. And, oops, sorry, that makes it kind of hard to see. And the pressure reading was 1.4582 ATM. So let's look at this differently. What if we have 40.7 milliliters And the initial pressure was 1.1042. So this is like pressure 1. Sorry, this is volume 1, and this is pressure 1. And then we have volume 2. Let's actually set this up differently. So we have 40.7. So here's our volume 1. And that's going to be the case every time. And we have pressure 1, which is going to be the same every time because it's still my house. And we have volume 2, which was 30.7 milliliters. And what was the pressure at 30.7? Pressure 2 was 1.4582. Okay. Then we had volume 3, which was 20.7 milliliters, and that had pressure 3 of 2.2003. Okay. And then we had volume 4, which was 50.7 milliliters, and pressure 4, which was 0.8828 ATM. Cool. And then we had volume 5, which was 60 milliliters, 60.7 milliliters. And why is it 0.7? Why do I keep adding 0.7? That's to account for the volume inside the box. How do I know it's 40.7? Because that's what they told me in the literature for this particular gas pressure sensor. They said, hey, the internal volume of this is 0.7 milliliters. Cool. And pressure 5 was 0.7225. Okay, here's what I want you to do. For each one of these trials, what I'd like you to do is first we'll do volume over pressure. What does that equal? If we take the volume and divide it by the pressure all the way down, then I want you to do pressure divided by volume and do it all the way down. And then I want you to do pressure times volume and do it for each one of these. Let's see what we get. So grab a calculator, take the volume, divide by the pressure, take the volume, divide by the pressure, take the volume, divide by the pressure, and so on. I'm gonna go get a calculator to do it too. $40.7 divided by 1.1042. I'm just going to go with 3 sig figs. Okay, so far, I don't see any really significant trends. It's like if you take the pressure and you divide by the volume for each one of these, we get a different number. Well, what if we take the volume and divide by the pressure? Every one of them, a different number. What if we take the pressure and we multiply it by the volume? Let's see what we get now. 40.7 times 1.1042 is 44.9. And then just keep going. Multiply them all. But what are we noticing now? If we take the pressure times the volume, we got 44.9. If we took the pressure and we multiplied it by the volume, we got 44.8. We took the pressure times the volume, we got 45. Let's just round these to 2 sig figs. We end up with 45, 45, 45 or 46, 45, and 44. This is not insignificant. Yeah, we totally could calculate it when we peg the thing, but we're actually trying to determine experimentally what is kind of, how can we make real predictions? Because see, here's the thing. We could make predictions because we find out that pressure times volume always equals a constant. So what we're finding is if you have pressure 1 times volume 1 at this particular temperature and this number of moles of gas, it's going to equal about 45. If you take pressure 2 times volume 2, it equals 45. Pressure 3 times volume 3, it equals 45. From this, we can say any pressure times any volume, given the number of moles and the temperature of gas that we have, is equal to 45. So that means P1V1 is equal to 45. It's also true that P2V2 is equal to 45. So we could simply say, hey, get rid of the stuff in the middle. P1V1 is equal to P2V2. We know this is true. We can find out that this is true just with a simple experiment that we just did. That no matter what the pressure and volume is, if you multiply it together, it equals, at least in this case, given this size of container and this temperature, it equals 45. So any pressure times any volume equals some constant. In this case, the constant is 45. So it doesn't matter if it's P1V1 or PNVN, it's going to be equal to K. Oops, sorry. It's going to equal K. So back to your comment, Ben, is couldn't we figure out or calculate what the pressure would be at 15 and 10? Yeah, we can. And the reason why we can is because we know that P1V1 is equal to any other new set of conditions. It's true that P3V3 is equal to, P100V100. It doesn't matter which experiment you do, they're going to be the same. So, do you have any questions about that so far? All right. Well, please finish up your lab, and I guess that's kind of it. It just feels so much like goodbye. Before you go, I just want to remind you to turn in your textbook, and if you're desperate to get your goggles, let me know. I'll figure out a way to help you get your goggles or anything else in your lab drawer. And also, if you're interested in doing independent research, send me an email so we can figure out how to get that into your schedule for next year. And I don't know, other than that, I guess that's it. I guess I'll see you guys next year, or if you're graduating, I'm gonna miss you. Goodbye. I've never had an end of a class on a computer like this before, so I'm not really sure how to do it. Thank you guys for coming over these last weeks. It's been really challenging for me as a teacher, and I'm sure it hasn't been easy for you as a student, but I really appreciate you guys sticking together and coming every morning. It's pretty unusual, I think. You know, most of this has been voluntary, and yet you still come. I think that speaks just enormous amounts about your dedication to your education. And I was looking through the labs or the quizzes last night, and I was just so proud of the work that you guys have done. I was thinking about if you had tried to do that on the first day of school, how well it would have gone, and it would have been terrible. And it really demonstrates how much you've learned and how proud I am of you. So I don't know. I'll if you guys want to sit and visit or something, I'll leave the Zoom open. But otherwise, I'll see you guys later. Have a good summer. Good luck with whatever comes next for you.
Thank you, Mr. Wright.
Thank you.
Mr. Wright.
Thank you, Mr. Wright.
Thank you.
Thank you.
Thank you,
Thank you, Mr. Wright.
Thank you, Mr. Wright.
Thank you, Mr. Wright.
Thank you, Mr. Wright.
Bye-bye.
Bye, Mr. Wright.
Take care. That this side has more electrons than it does protons. So it has a negative charge, and this side has fewer electrons than it does protons.
It's a smash hit.
For today, I'll see you guys later. Take care. Bye-bye.